Thank you very much, Victor. But I have left QUT, Queensland University of Technology. I'm now heading up my own research group, so just to bring it up to date. The first two slides are completely irrelevant, but they're to try to put the philosophers at ease. I hope you recognize the house that Wittgenstein designed for his sister, Margarita Stoneborough Wittgenstein. I visited it for the first time only about 6 weeks ago, and I must say, actually, I was very impressed with the architecture. I wasn't expecting to find something that was actually really quite so exquisite in the kind of architectural terms that I know. The light inside was superb. It had originally had this extraordinary stone-coloured textured walls. But the most extraordinary thing was the detail that Wittgenstein had designed all the ironmongery, all the locks, with painstaking care. And it was worth it. It really showed the results of this care. So it was very interesting seeing that mind from a domain which I confess I know so little into a domain I feel I know quite a lot about. And it was clear that there was original and interesting thinking being brought to bear in this house, although it was clearly in the style of Loos, who had done so many of the coffee bars in Vienna. So in that sense, it was derived architecture, but nevertheless, he made it his in a very interesting and original way. Right, that's all I'm going to say about philosophy, because that's all I know. A problem. Now, we are faced with what I see as massive problems which architecture could be addressing better. And why? Because architecture, building, the built environment, consumes an enormous amount of our resource. More than 50% of our energy goes into constructing, building, maintaining, heating, cooling, powering buildings, and demolishing them again. And it has a massive social impact, obviously, a massive impact on the way we live. And we could be doing far more about it. There is no reason whatsoever why every building shouldn't net export energy to the grid rather than consume it. It could even export enough to pay for all the energy required to process up the materials and to construct it. There is no reason why it can't do this. But there are lots of reasons why it's not happening. And to take it further, whole cities could, and eco-positive, of course, is a made-up word, doesn't mean anything, but the obvious implication is it could make a positive contribution to ecosystems and the environment and ecology rather than having a very destructive influence. And with now more than 50% of the world living in cities and possibly 75% by 2050, this is a massive problem to which architecture could make a very much bigger contribution than it does. And we've got very powerful techniques to bring to bear on it. We have fabulous new computer techniques which could help to accelerate the rate at which architecture impinges on that environment. But I will argue that there's being significantly squandered on trivial projects, beautiful stylistic ideas which are poetic or maybe very appealing visually and spatially, but that do not address any of these key issues. And while some of the architects that produce these works are very close friends of mine, I have to say it every time I meet them. It's a continual battle to try to persuade them to apply all their energy and talent to real global social environmental problems, rather than just being concerned with creating new stylistic isms. What does massive computer power do? Well, lots, but I'll pick on four things. The temporal compression of space and spatial compression of time means we can build models of very large things in a very small space in the computer. We can model whole cities, or even whole cities in their footprint and their hinterland. We can compress time, so we can look at the evolution of a city over 100, 200 years in a few minutes on the computer. Nature employs ruthless prototyping, actual prototyping, and all the failures, of course, just get eaten. It's been very unfashionable in architecture to do real prototyping. The Middle Ages did a lot. Almost all the cathedrals fell down at one time or another. This has been rather covered up in history, except those that fell down late. There's some very interesting examples that fell down 60 or 70 years after they'd been constructed. And that rather got out of fashion then, so that after that people tended to build more conservatively, whereas, of course, the Gothic cathedrals were a race to build higher and more spectacularly with more and more light coming in the walls. So computer allows us to virtually prototype. So instead of doing one-off buildings, we can explore multiple possibilities in the computer and analyze them and test them and explore them for their behavior, for their use of energy, everything before we construct them. And we also now have increasingly direct computer control of the means of construction, so that the actual inefficiency of the building industry can start to be addressed. And it also gives whoever is in control of the whole system, and I'm going to talk as if that is the architect, but it isn't necessarily anymore always, it might be an engineer. And I'm also involved in other design disciplines. The 3 schools of which I've been head of or dean have all had in other areas such as industrial design, fashion, graphics, and interactive design as disciplines within them, as well as the architecture that I'm most familiar with. So although I will use architecture as the main term for simplicity this evening, I think you can read design or other disciplines pretty well consistently throughout. So what questions did my students, I've been with them 3 days now, and they've been very patient, and I asked them to formulate the biggest questions that they could actually manage to address. Rather randomly, we picked, as a group, that is, with their consent, the 3 questions at the bottom. But they were about what are the designer's role in this evolutionary process that I'm about to describe. Could we make a process that produced environmentally beneficial buildings and so on? Could social values be used as part of the determining process and so on? There were a list of about 20 questions which they've been discussing and are going to continue to explore. So what are the problems with architecture as a discipline? Well, it's pretty bad, I have to say. We have no defined design process, full stop. We have an absolute lack of relevant theory, full stop. We have a disastrously backward building industry, and we have, I've just pointed out, an industry which makes massive social, environmental, and economic impact. Now, of course, we can also turn this round and see those as 4 opportunities for us to make some interjection and change into the process. And that's very much what I was trying to encourage my group to do, and I hope that's what they will continue to do. It only seems to have recently come to anybody's notice that the construction industry is so primitive. But recently there have been an outburst of books like this. It's extraordinary. If you compare it and just think about how you see buildings constructed, compared with anything else, it's so far back. Well, why? It's a lot of reasons, and one of which, of course, is it's very capital intensive. Equipment like tower cranes are very expensive. Starting to bring robotics on site is going to be very expensive. But we're starting to see change there. So there's an opportunity, there's a problem there, but also it's a possible driver for change. The theory. The theory is incredibly disappointing. I don't know whether you've ever looked in Vitruvius's 10 books. The book on the education of architects is quite nice, where it explains why we have to do music, of course, and astronomy. But basically, it is of no actual help. Alberti, which Neil showed you 2 days ago, and of which he very modestly didn't really point out, he's one of the key translators. First of all, it needed translating again, because the edition I had as a student was written so much from a historian, translated so much from a historian's perspective, that it was of very little use to a practicing designer and architect. But when you start to look inside, it's got about 12 very elaborate engravings. And what are they of? What do you think that elaborate... Someone's got a lot of trouble to do that. What does it tell us? It tells you how to support a heavy weight with 1 rope. And why would it do that? Because on the next page it tells you how to do it with 2 ropes, on the next page 3 ropes, on the next page 4 ropes, and so on. Well, it explains pulley systems. So these enormous engravings, all this trouble, that's all it's explaining. And whilst I'm being a little bit unfair to the book as a whole, it actually doesn't tell us very much more. So we don't really have an existing theory. And what theory we do have has been very badly translated. Le Corbusier's There's an Architecture was translated when I was a student as towards a new architecture, which puts an entirely different spin on it. And the whole of the rest of the contents of this book, of which a whole generation were brought up, bear very little understanding of the concepts that Corb was putting forward. So first Le Corbusier was advancing quite controversial ideas, but on top of that, they were totally mistranslated. So there's confusion on confusion. And our historians haven't done us good service either. It's what I call the toothpaste history of architecture. where somehow every building, every ethos is treated in this same manner, and mostly by historians with no technical understanding at all. So technically advanced buildings often got left out unless it fitted into this theoretical apparatus that they'd invented for themselves. So basically we've been badly served in every possible direction. And we've also been badly served by our clients. That is King's College, Cambridge, that's the chapel. And it could have been a very fine building. It is actually quite a fine cowshed. But it went very badly wrong because the fellows of King's College at the time were influenced by fashion. I'm just going to have to explain this technically a moment. The original vault would have sprung from the top of this arch and formed a smooth surface which took the light from this window across the surface of the vault. But unfortunately, fan vaulting came into fashion. They heard somebody at Ely or wherever had built a fan vault. So they had to have a fan vault King's. But unfortunately, a fan vault wouldn't fit because they got this already this far. So the only thing to do was to infill with this hideous spandrel panel, which completely stopped and interrupted the flow of light. Second problem, the ribs traditionally run all the way through the ribs of the line due to various principles which are basically borrowed from medieval philosophy, scholastic philosophy. Things like deductive cogency and mutual inferability, so that from one section down here, you could infer the construction of the vault. Well, look what's happened. Because it suddenly got to spring all these ribs, there's a horrible fudge here. No. So anybody of any sensitivity going into that building, instead of being awestruck, they're horrified, and all their nerves jar with horror. Hideous. Look at that. I mean, I hope you're all in pain. So that's clients for you. They get distracted by fashion. Then there's another problem which is about values. No, you don't share values. This particular issue of New Society had an article in it by 4 people of whom I have great respect: Rainer Banham, Cedric Price, Peter Hall, Paul Barker, which advanced as an argument that the present planning constraints weren't working, and you'd be better off if you had no plans, and went into an experiment. And they described how you could have a much more flexible and open planning system. The attention to flack that this attacked with this article was quite extraordinary. So it was difficult to even advance different ideas about how we could operate politically. This isn't anything to do with architecture, it is to do with the planners and the government imposing planning schemes and restrictions, which actually impose restrictions on our environment, which are causing a lot of the problems. But it's very difficult to persuade anyone to address it. And there's another example here of values. I think I'll let you read this. I better explain first. The Think Belts project is a project by Cedric Price, who was one of the signatures to that article I've just shown. And the Think Belt potteries, he was suggesting that an area of Middle England where there had been a very thriving potteries industry, which was then defunct, that all the railways could be redeployed as a new form of flexible university. Very interesting project proposal. But as the quote says, it stopped well short of offering the occupant an ashtray on the grounds there is no guarantee the designer and the occupant have the same cultural values. Whereas at CBS, very famous building in New York, designed by Eero Saarinen, control freak, they only allow him one, approved by Florence Knoll, on the same grounds. There was no guarantee that they shared the same cultural values. So we have a problem about not only the client, but the fact that the client is often not the user. It's going to be someone else. So what assumptions do you start to make about the user's cultural values? And of course, I don't usually show cartoons in lectures, but I couldn't resist this. I thought it caught so beautifully the problem of the image of the modernist architect and the clash between the expectations of these two little dear clients and the pontificating architect. And it's still going on. And next slide, I better warn you in advance, is Zaha Hadid. Now, Zaha's a colleague of mine. I used to teach with her. She's kind of friend. And I like her work enough that I just have spent the entire fee for coming to these lectures on one of her artworks. So there's someone I respect and like. However, when she's got the Pritzker Prize, which is the kind of Nobel Prize at architects, one of the highest awards in the world for architects. When interviewed on British television, it's not that often that they interview a female architect. She said this. And she was just being herself, but didn't seem to even have the humour to understand the kind of impact her what were read entirely as being extremely arrogant remarks were. And the scale of her buildings. The Olympic Stadium in Tokyo is hers, for example. Buildings on a vast scale. And of course, needing very, very powerful computer techniques that I am interested in, but I do wish they weren't being used for those kind of projects, shall we say, discreetly. I'll compare or contrast Zaha with another friend of mine who I also taught with, both at Cambridge University and at the Architecture Association, and also lives in Australia. Britt Andresen, she's also extraordinary. She was the first woman to get the Australian gold medal for architects. After 100 years of giving it to men, they finally gave it to Britt. And Britt is the absolute contrast. She lives in a very modest house. I'll just show quickly a few slides of her house. Timber construction, open frame, lightweight, thin members, casual, an ambivalence between inside and outside, rough, unstripped timber, gallery spaces, completely unconventional plan, two-story spaces that open up so you can't tell what's inside and what's outside, and then long, thin gallery leading out into the Pacific Ocean. And this is like a pencil sticking out of the hillside, where all the adjacent houses, of course, are across the hill in order to maximize the window space that looks across the Pacific. By doing it this way, of course, it stores this incredible surprise. You can see the glimpses of the sea at the far end of this structure as it goes up out of the hill. So these are extreme contrasts, is the only point I'm trying to make. Contrasts of attitude within the profession, contrasts of attitude in society, contrasts of attitude of the clients. And then, of course, there always were other things. There was always the vernacular, the unplanned, the unscripted. And, of course, these are the things that tourists generally take the photographs of. So, to quote Cedric Price again, it's the third time I'm quoting him so far, in this case to misquote him, he actually said, technology is the answer, but what was the question? But in this case, I'm posing the question to my group. Computing's the answer, that's because that's what we say we're doing, but what was the question to which it's the answer? Or to rephrase it, what exactly was it about designing that needed aiding before we had computer-aided design? Because we got that solution before anybody had clearly formulated the problem. And that, of course, is, you can imagine, extremely dangerous situation. It's easier for you to see. So what was a disadvantage to me then now is a tremendous advantage. So you can see I could bend it, but not actually bend it. It's all actually only made of those units. So it was all to do with rules that allowed me to do various things like stretch, bend, and so on. And so that meant a whole new attitude to how your building model was constructed. There's the data structure, and instead of putting all that in, you had the seed, and you had this cultivation program which gradually grew this data structure until you got whatever you wanted, and then and only then, because you were only dealing with one tiny spot in space, which we called a moat, which contained all the information about that unit, and which way up and which way round it is, all packed into one word of Atlas Titan machine code, and out came the buildings. So these are more complicated maneuvers, you can see pulling up, stretching, so on. And out of that, we could generate perspectives and plans. And this drawing, for example, if you compare this one with this one, they've both come from the same seed totally automatically. I haven't put all that data in, I've just said, go, stretch it. And the whole idea was to get to a point where I completely could automate it. That's a later one when we got better computer screens. By the time we could get a complete computer screen, see the whole thing. This is a bit of a sidetrack. It's just that I am plagued with people who tell me what I'm doing is a shape grammar or space syntax. It's nothing to do with either of these things. I wrote 2 graphics languages in my life, the shape processor language, SPL, which was a complete interpreted language just for manipulating shapes. It was a shape processor like a word processor. It manipulated shapes like words and allowed you to draw these things. And the genetic language of architecture was later. That was for these genetic manipulations which we're about to do. And that's what it looks like, and you don't want to know about that. So now we come to two important things, generative techniques and learning techniques. I have this thing that any piece of software that's going to be any use, we can't write. All we can do is write the structure for it, and then it's got to learn how to develop itself, to be anything like powerful enough to address any real interesting problem. Now, there are a whole pile of these generative techniques, and I'm only just going to touch on two of them. I have to mention parametric, because that's key to all of them. And Patrick Schumacher, who's coming later in this course, he actually will talk almost exclusively about parametrics, so I shan't say any more now. Down the bottom here, we have procedural shape languages, which is a technical term that computer experts use for my system. I didn't give it that name, that's what the literature calls it. And down the bottom, we're going to have a little bit of polyautomata and cellular automata for a moment, because they're very simple ones to explain, and we spent quite a lot of time the last couple of days playing with them. So here's one with my students, where it starts, a cellular automata is a very simple thing. There's a grid of cells, usually 2D, but of course we were interested in 3D, and each cell looks at its neighbours, and each of these cells has states. Now you may know something called the game of life, where things have two states, alive or dead, and they have 8 neighbours around them, and if you have too many neighbours, you die of suffocation. If you have too few, you die of loneliness, and if you have exactly the right number, you can be born. And it has some very surprising emergent behaviours. Now these ones are exactly the same, except in 3D, and with many more states. This particular model is running with 4,096 states and a very, very large number of transition rules. Each one has a state. You have transition rules, which are alive or dead or whatever you're going to do next, and you usually have a clock. And in this case, we had a clock. And so these are the steps that this is going through as it develops in space. Now, you all start off as one cell, and that cell splits and splits and splits until you become yourself, and that's exactly what's happening here. Also, all your cells are identical to begin with. In this case, at this point, they've started to specialize, which again, and so they're starting to take on colors and different shapes. So each cube is no longer being a cube, it's starting to stretch, it's trying to shear, it's starting to change color, all right? With a bit of luck, this might run. This is a little slow, so I can catch my breath. It's slow because we didn't have much computing power then, and this is as fast as we could make it go. It's looking at its neighbours and its rules, and as a result, deciding what steps to take next in its development. So this isn't evolution, this is development. This is the developmental process by which you go, every plant, every animal on the planet, goes from being a single cell to being a multi-celled organism. It's like making paint dry. Sorry about that. There's no way I can speed it up. We just have to hum or something for a moment or two. Or think of nasty questions to ask me at the end. Okay, at this point it's going to start to specialize, and each of those cells is going to start to change color, change geometry. You'll see it sprouting things at the top and bottom and so on. So from starting just with one cube, we can develop into increasingly complex structures. It's still quite a long way from being a building. For a start, it doesn't touch the ground. It appears to be flying, but we got there eventually. It just took a while. We'll get there in a few more slides. But these were early experiments with this group of students trying to get these things to run at all. And each time you run this program, it produced something different. And that was controlled by the other part of this, which is called the genetic algorithm, which is more like the evolutionary change rather than developmental change. Okay, so each time's different. And then then it occurred to us to start putting the intelligence inside the cells. So this is technically it's a reconfigurable array processor. Inside each of those cubes, there is a small integrated circuit and 8 light-emitting diodes which show you which state it is. So this could have, each of these cells could have one of 256 states, and it passed messages up and down the stack and through an intelligent baseboard, rather like that Walter Siegel model I showed a few minutes ago. It has all the wiring in the baseboard, and each of these cells can talk to each other and determine their own configuration. And that was built again by a group of students working together. And the lights, there was no robotic control arm or anything. The lights flashed to solicit you to please interact and take a cell away or add another cell in determining what it was trying to do as it tried to arrange itself. So that is one very simple example of a generative engine, okay? It's something that can make something more from just one seed. And of course, these become more complicated as the years go by. This one is the first example by a student who really combined the environment here, which is being simulated, with the genetic algorithm. And these are envelopes of ideal shapes for the environment they're trying to create. I think I'm going to skip past this a little. Next step is embedding intelligence, which you just started to do there. Well, what happens if you embed it in the whole fabric of the building? Cedric Price, we've mentioned him several times before, project for which I was one of the consultants in Florida. He asked us, he had all these little cabins on site which could be moved around to suit changing needs of the building. The client, Howard Gilman, wanted this to be used for different things like recreation for his employees or instruction for his employees or all kinds of things. And that crane, the idea was that crane was going to stay permanently on site and in response to a set of instructions, drive around, move all the units and reconfigure the site. He asked us to write the computer program that would do that from the instructions, so we did. And I'm not bothered to show you that because that's trivially obvious. All it does is work out how to arrange the bits. Well, you know, any idiot could do that. But then I said, well, look, why don't we put the intelligence actually into the structure? So I built a model of it. That's the model. There's a tiny part of the site, just a 4x4 part of these array of columns, and these represent the little cubes, and they're all connected to a controlling processor, which of course knows where they all are. The screen resolution is so bad on this cheap computer. This is a Commodore PET. You're all too young. Personal electronic transactor. Never caught on. PC's much more personal computer. PET. Anyway, personal electronic transactor. And look, it's 8K. And that's its memory. So it's driving a laboratory plotter, which is actually producing a perspective of the changing configurations of the units, but of an implied much larger area. And I said, look, sorry, we can build an intelligent model to interact with instead of having the person running the site having to just move these things around. But why don't we put them actually in the structure of the building? So the building itself is literally intelligent. So he and the client said, yes. So here we go. Oh, this is just showing some cladding panels. That produced the usual plethora of slightly misleading, more than slightly misleading, press comment. But this was the first building to be dubbed intelligent by the press, at least. But there's one more twist to this. I realized there was going to be too much intelligence by the time we'd put one of those chips in every single part of this building. What were we going to do with too much intelligence? Well, you know what you do. You get bored, don't you? I'm looking around the room. So the crane driver's got an instruction to move that cube. But it might just be that that cube has got bored with being where it was. So it's mischievously sent instruction to the cube driver to move it. Now, that is not as silly as it sounds. The reason was, there are two reasons for this. One is that Cedric and I were both worried that people weren't used to changing their building, and once they got an arrangement they liked, they might leave it like that. And he wanted these things to be moving on a daily basis. So part of the intention between this was to provoke the users. Say, don't move that, put it back, so that, But in doing that, the computer program would start to learn. And so the idea was that it was going to try to learn to be able to lay out the site better than we could in our computer program. So that's the beginning of the notion that computer programs really ought to learn. So this also got some rather curious press comment about the notion of this building that got bored and started to draw its own plans. Well, I think all buildings should start to get bored. If they got too bored, they should knock themselves down. Genetic algorithms are how we drive this. They're attributed to someone called John Holland. They're developed for optimization engineering, and we said we're going to use them for design problems. Everyone said I was an absolute idiot, as usual. And because, sorry? Missed that. Because design has ill-defined problems and conflicting criteria, and there is no way these algorithms could cope with that, or so they thought. And a typical example, here's an example. There is the outside of the boat wanting to be as streamlined as possible, to go as fast as possible. There's the inside of the boat, which wants to be spacious and light, an area for the cruisers to be in. And what happens with the genetic algorithm? It gradually makes the boat longer and longer and longer, and thinner and thinner and thinner, until it's completely useless. So we had to deal with that problem, and here is the answer. This is a crucial slide. Up to now, all the engineers were in this corner. Convergent evolution and natural selection, by which we mean by calculation in this case. So they're in this corner. They had never thought there were three other corners in this matrix. And I added artificial selection, and I added divergent evolution. Artificial selection, if we're talking about the boat, simply means you get the computer to print out a whole sheet of boats, and you pick by eye the ones that you're going to breed. And now that, of course, is exactly what Darwin had done. That's just a bigger version. Darwin, faced with the problem of explaining natural selection, starts the book with variation under domestication, which in this case I'm calling artificial selection. He said, you know how to breed faster horses or racing pigeons or more beautiful Labradors or more hideous Pekingese or whatever. You know you pick them and the breeder, and that's called natural, that's called domestication, artificial selection. Sorry, thank you. And then by the time he gets to chapter 5, he said, but that's how nature does it. It's just that it takes a lot longer. Nature has all the time in the world, and it profitably prototypes, and that's natural selection. So all I had done with this was, in fact, added back, go back that diagram, I'd added here the artificial selection, which is, in fact, the first chapter of Darwin, where all the engineers had gone into this corner. And this meant, these selections meant that we could use both our intuition and our judgment, as well as the ability of the machine to do complex calculations. And if they were all getting in a rut, you could turn up the amount of genetic mutation there was. And that would then generate a massive population of very different things. This is what you did when visitors came to the lab. You cranked up the divergence, and it comes with all these wild ideas now. Oh, isn't it creative? Well, yes. Okay. So the next step is so that's the selection that's going on there by either artificial or natural means. And here's an experiment running that. We had an exhibition in 1995 following the publication of this book. No, this one was running for this book, but it's not in the book because it was running while we were doing the exhibition. This thing evolves from top left to bottom right during the exhibition, with the interaction of visitors to the exhibition, people on the internet. Now, the internet, for most people, only really started to happen in 1994-ish. This was January 1995, so it was really quite early days. And this is the first exhibition you could visit virtually online. And not only that, you could interact with it virtually online, and people did. Let me just go through this. So step one is this is also happening in an environment. It measured the atmosphere of the exhibition space. So the environment is how much smoke there was, how much noise there was, and so on. And there were eight environmental factors which were affecting the environment. So those are all the messages coming in up there, plus there were switches in the exhibition space, so you could actually go in and switch the genes on and off to see what happened. And those are other instructions coming on the internet. That's the single cell dividing. We've gone off cubes and gone to spheres now. A sphere is much nicer, has 12 neighbours, which are all isomorphic, isotropic, everything. And that's the resultant form. I'll just stop that. Just go to this, which shows you those cells in a bit more detail. This is you, starting your life, one cell. And then there's all these transition rules, and that is growing into some more and more complex form in accordance with transition rules which are being switched by the genes, and I'll stop that. And then there's some output, you materialize it. And this is not a building proposition, it is the shape of the data. That's all it is is. And this is what evolved over the course of the exhibition. And this, in fact, was using the top left-hand corner of that matrix, and the criteria is evolving forwards increasing complexity. If the particular gene combination produced more complicated and more tangled up forms, we decided we would reinforce that piece of genetic information. Okay? The complicated, very complicated software, this, with many evolutionary cycles. We went on to other things like towers. This is a real project for an architect called Chris Muller. The only reason for showing this is quite interesting. There were supposed to be 4 towers, but the software at this point has, of its own accord, decided to join these 4 towers together into one. And it has another run of the software where it's done the same thing, it working out that that is the optimum shape for it. So we're now talking about those building models. We've done the electronic craftsman. We've done building information models. I'm now going to touch on closing the loop. How do we complete this cycle? BIM, this is this technique that's used, building information model, has this big problem, how you get the data in, and what do you do with the results of the analysis, because it's a passive tool. So there are various ways you can build up the amount of cycling and automation in this till you get to this diagram, which is what we were leading to, where we had a completely automatic model builder. All the problem of putting all the data into these models was skipped, and it went straight to building a model automatically, a simple model, which was the basis of the analysis, and then it went out to something from which you could construct the building. And only others were kept for future possibilities. So here's an example. This is a project with Patrick Jansen, who was one of my PhD students, and later some of this work was done under research grant when I was working with him. None of those have been designed. They've all been evolved by this process. Combination of a cellular automata type thing with a genetic algorithm. And here it's working. Automatically, totally, of course. What do you want? Well, I want to build a house. So you've told it something about the rooms, so it puts some staircases in, all by itself. Cuts some holes through it, makes some spaces. And then when it's finished producing one, it then starts to analyze it. Here it's just adding the fenestration. So it starts to analyze it for its performance. And in the early stages of this, if I can get this to stop, it's analyzed, well, this is just how it works. We've got generative techniques plus evolutionary techniques plus environmental optimization now. 3 things running together. There's some genotype information building, driving a development of a plan. Here is various kinds of analysis for its thermal performance and so on, which gives it a fitness function, a measure of how fit it is to compare with the others. So let's click on the switch and run 10,000 more and see if we can do any better. And there we are. Up here, we have hundreds of them, what's called a Pareto optimization graph, and all these along this edge are good for one reason or another, different reasons, and you can select which of those you would prefer, and all the ones up here are absolute duds and should be trodden on. And then it does the same thing, crossover of the genes, and so on. And so this is the control variability of those experiments. And then gradually we added more and more things you could measure, to do with the structure, to do with all the things to do with the services, to more and more of the quantifiable criteria, and still unquantifiable criteria we were still doing by judgment, by the artificial selection. So that's that total process. So that's the whole thing summarized that I've described. So I've got one more thing to show. Oh, there are a lot of tools we've got for that, but we can skip these. We work in what we call an isospatial environment, which is simply a close packing of spheres. Universal state space modeler, which is equal in all directions, equal in every way, which is very nice to work with. And that's how these layers work. And so we defined a mote, which is a little point in space, which knows an awful lot about itself, and it communicates with its neighbors through these logic fields where information flows in 3 dimensions through these meshes of spheres. But they're not really spheres, they're tiny points in space. Now, I'm now going to show how that's applied, and we're finished. This is another of my students called Gianni. And Gianni here is building an active tool as opposed to a passive tool. In this tool, this gives you information before you design the building to help you design it rather than analyzes it afterwards. Okay, so each of these points in space, and they're drawn as little spheres, but they're really just tiny points, knows everything about the solar conditions of that point in space. How many hours of sunlight at what time of the year, and so on, for this particular site in Groningen at latitude 53. It knows everything about those so that you know and understand and can start to make envelopes of possible shapes within which you could construct something which would have optimum solar penetration, shall we say. And he called all that solar logic, and that was to do with being able to drive the generation of form mostly from the solar direction. And here it is one of them being built. Now, this site's a bit curious. It's in Notting Hill Gate in London. The client owned a factory in the centre of here and persuaded somehow the planning authorities to allow him to build a house in here. There's houses all the way around it. It's most extraordinary it's ever got planning permission, but it did. The condition, though, was that it didn't have any windows, because then it would be looking out on the neighbours, so they all protested there aren't any windows. So he built an entirely windowless house. But the client wanted sunlight in all the rooms, including the basement, where he was going to have a swimming pool. So Gianni, we built this model, right, where this is to explain to the client what's going on. Each of those is one of these motes in space, and each of those knows more easily so that the results of their calculation when you go and look at a student project and they use these calculations and it shows there's not enough light, then they say, what do you do then? They said, well, I don't have time to do anything else, you know. I don't think of making the window bigger or anything. So that you've got to get all these things built into the system automatically. And that's why I think seeing very successful demonstrations like that, which are very publishable and very photogenic, does help to raise the interest level about these things. That's my hope. Otherwise, can't justify those projects at all. And I think the client for that building would like to see wider application of some of that thinking. And if it's any consolation, the same architect, Gianni, went on to win a major award for his next project, which was not top lit. So in a sense, he learned something. And it wasn't for a stinking rich client either. It was a fairly modest house. So, I mean, I'm obviously an optimist. I obviously believe that some of these tools could help, but I'm depressed by political pressures and economic pressures that make it very difficult to deal with real social issues and real environmental issues. But I think the pressure is going to grow and grow and grow about the cost of housing and about the environmental issues to the point where just the voice of all of us does something like affect the politics. I hope. Isn't that what democracy's supposed to do? And I don't know. Is that all the questions we can have? Right.